Hello, I'm Nuno Carvalho, and today I will be going over the answers and my worked out solutions to all the multiple choice questions on the 1993 AP Physics C Electricity and Magnetism exam. Throughout the video, unfortunately you can hear my chair creaking and my desk creaking as well. I apologize for that, my microphone's not that great, but other than that, I hope you find this video very educational and helpful for your studies. Thank you. Starting with number 36, we're asked, from the electric field vector at a point, one can determine which of the following, and then we're given three different statements there. But so let's begin with this. This is the information that we're given. We're given an electric field vector that would look like this. And so for statement 1, the direction of the electrostatic force on a test charge of known sign at that point, we actually would know this information. If we know that there's a positive charge at that point, then the electric force will be in the same direction like that. But if it happens to be a negative charge, then the electric force will be in the opposite direction. So we would know the direction, so we can mark that as a yes. For number 2, the magnitude of the electric force exerted per unit charge on a test charge at that point. The key word here being per unit charge. So you might know from your formula sheet that this is the equation for electric force. It's Q times the magnitude of the electric field. And so if we are asked for the magnitude of the electric force per unit charge, then really we're asking for F of E over Q, which if you look at our formula here, well, that's just going to be E. So the magnitude of this will be the same as the magnitude of the electric field. So we can also know that because, by the way, we can tell the magnitude from the length of the electric field vector right there. And then for number 3, we are asked the electrostatic charge at that point. We will not know this information. The reason for that is that an electric field vector can occur at a point even if there's no charge there. It doesn't really matter what the charge is. Necessarily, the electric field vector still exists in space no matter the charge that actually exists or doesn't exist at that point. So we don't know that. So the answer here will be C, which is 1 and 2. For number 37, we are told that a circular ring made of an insulating material is cut in half. One half is given the charge negative Q, uniformly distributed along its arc. The other half is given a charge of plus Q, also uniformly distributed along its arc. The two halves are then rejoined with insulation at the junctions J, as shown above. If there is no change in the charge distributions, what is the direction of the net electrostatic force on an electron located at the center of the circle? So the key words are here that there is no change in the charge distributions, which means the charge distribution we see here stays. And also keep in mind this is an electron, and that's going to be a big deal. So we're told that it's located here at the center, so around there or so. And then we have to be thinking basically these tiny charges here that are all along this ring, what type of electric field vector would they be creating on the center? And so what you have to know is that since there's sort of this symmetry along this axis here, there's going to be no horizontal electric field. It would only be vertical. So we can already just eliminate any type of, answer that goes to the right or to the left. And it's really not going to be going into the page. That's also another dimension here that is not really relevant. So now we just have to think, is it going to be going to the top or to the bottom? Well, we know that electrons are attracted to protons, right? And so we know that it should be going to the positive side. So the electron would experience a force in this direction. But we can also just be thinking about the fact that the electric field, the protons here will be creating an electric field vector that would be going in this direction. It would all the other horizontal components will be canceling out, so we can just ignore those. And the negative charges will also be doing the same thing, going in that direction as well. So if that's the electric field, well then the electron will be feeling a force that's opposite in direction of that, so it must be in that direction. So the answer here is towards the bottom of the page. It's B. Number 38, we're asked about the net electric flux through a closed surface, and we're given a bunch of statements here. But let's first just think about the equation for the electric flux. And so given Gauss's law, you'll actually be using this statement right here, that the integral of E over a certain area will equal to the charge enclosed over this constant right here. And really this middle formula here is not important. We just have to be thinking about this and this. And so given this, you can easily see that if the charge enclosed is 0, then our electric flux will equal to 0 overall. And so we can actually already skip to part E here, or answer choice E, I should say, and know that that's going to be the right answer. All the other answers here don't really make sense and don't align with Gauss's law. For number 39, we are given a circuit with a bunch of capacitors, and we're asked for the equivalent capacitance of the system. Well, what we need to know is how do we combine capacitors that are in series and in parallel. And so when they are in series, then we use this formula right here, that the equivalent capacitance is going to be 1 over C1 plus 1 over C2. And then when they are in parallel, then it's going to actually be much simpler. The equivalent capacitance is just C1 plus C2. And so on. We can continue adding here more capacitors as well. So before we completely figure this out, we need to know, do we first want to look across each sort of branch here in the circuit, or across the entire thing? And we usually just want to do across a branch like this and figure out the equivalence capacitance of that, and then sort of shrink down all the branches into one. So starting with just one branch right here, we want to figure out the equivalence capacitance. And since those two capacitors are in series, we use this formula here. And we are told that each capacitor here has 2 microfarads. So we can do like this. And what this is going to end up being is just, well, 1 microfarad, I guess. And when we invert that so that we just get the equivalence capacitance, well, we're just inverting 1, so we just stay the 1 here. So that means that each branch here has a equivalence capacitance of 1, like this. And if we connect them all like that. Okay, so the next step now is to shrink down, like I said, those into all one branch. And now they're in parallel, so this becomes much easier. It's just a matter of adding all the equivalence capacitance together. And what we get is that the overall equivalence capacitance is going to be 3, and the units here are still microfarads. So the answer is C. For number 40, we're still working with the same circuit from the previous question, but now we're told what potential difference must be applied between points X and Y so that the charge on each plate of each capacitor will have magnitude 6 microcoulombs. So we're asked for the voltage between this spot and this spot. And what's going to save us here is knowing that the voltage across each branch, so from there to there, or there to there, or there to there, is going to be the same as the voltage from X and Y. That's a property of circuits, that the voltage is going to be the same when it's in parallel like that. So we can just be thinking about a circuit that looks like this, and be thinking, what's going to be the voltage across those 2 points? Well, we still have a capacitance of 2 microfarads on each. And what's going to be very helpful for us is this formula right here, V is equal to Q over C. And this is in your formula sheet. And once we know that, we can actually pretty easily solve this question. What we just need to be careful is that if we're asked for the voltage across the 2 capacitors in series like that, then we need to find the equivalence capacitance, okay? The equivalence capacitance, not just the capacitance of 2 microfarads, it will be the equivalence capacitance. And if you remember from the previous question, the equivalence capacitance of each branch should just be 1 microfarad, okay? And so then that begs the question, what's the Q on this? Well, it's going to be the same Q that was on this one and on this one, because that's, again, a property of capacitors that are in series, is that they share the same charge. And given the question here, we're told that that's 6 microcoulombs. That means we can finally put everything together, and what we get is that 6 microcoulombs over 1 microfarad. That should be microcoulombs, my bad. Microfarads, that's just going to give us 6 volts, and so the answer is C. For number 41, we're told that 4 positive charges of magnitude Q are arranged at the corners of the square, as shown above. At the center C of the square, the potential due to one charge alone is V0, and the electric field due to one charge alone has magnitude E0. Which of the following correctly gives the electric potential and the magnitude of the electric field at the center of the square due to all 4 charges? Okay, so we need to be thinking about whether voltages and electric fields will add and cancel out. And so let's start with the electric field. I think that's maybe easier. If we think about the electric field due to just one charge, I'm thinking about this charge right here. That's the electric field that it creates, the electric field vector, and we're told that this has a magnitude of E0. Okay. The thing is that, well, that charge is basically canceled out by this charge, which will produce an electric field vector that's in the opposite direction and also same in magnitude, given that their distances and their charges are the same. And the same thing will happen for this and this, which basically tells us that the electric field will actually be 0 right there in the middle. It'll be 0. So we can already eliminate any answer here that doesn't include 0 as the electric field. So we're left to just A and D. And now let's think about voltages. Do voltages work in the same way? Do they cancel out because of symmetry? No, they don't, because a voltage is just going to be a scalar quantity. It's not a vector in the same way that an electric field is a vector. And so that tells us that if, because of these two, or this charge here and the relationship to this point C right here, it's given a magnitude, the voltage is given a magnitude of V0, and it's just a scalar quantity. Well, having 3 more charges that have basically the same distance and the same charge will mean that the overall voltage will just be 4 times V0. And so the answer here is going to be D. Number 42 is actually quite a difficult problem. We're told a large parallel plate capacitor is being charged and the magnitude of the electric field between the plates of the capacitor is increasing at the rate dE divided by dt. Which of the following statements is correct about the magnetic field in the region between the plates of the charging capacitor? So we're being asked about the magnetic field, and we're told this is between a capacitor, which is different than what we're usually dealing with when we're talking about magnetic fields. However, there is an equation that you learn in electricity and magnetism that's not on your formula sheet, but it's pretty important to know. And it's one of the very last things you learn. It's the Ampere-Maxwell law. And so let me write that name there. Ampere-Maxwell law. And maybe you didn't even pay attention too much. It's sort of something that you go over quickly. But the equation is this. Okay, so it is quite a long equation, and it's actually sort of an addition to the Ampere law done by the scientist Maxwell here. The key part here is this right here. It's sort of the addition that Maxwell added to the to the Ampere law that you'll probably recognize. But that's where this is all going to be coming in from, the answer that is, because then what we were basically saying is, well, the current inside of a capacitor is going to be 0. There's no current that's really happening there. But there is a changing electric field, at least in this situation here. And so that means that the magnitude of the magnetic field will be sort of proportional here to the d of the derivative, I guess, of the electric flux with respect to time. And if you think about it, well, electric flux is really just the integral of E over dA, which tells us that if the electric field is changing at a rate of dE dt, and assuming the area is staying constant, which for a capacitor it is going to, then that means that really this is also proportional to the change in the electric field with respect to time. And so if we go back here to the question, or to the answer choices, that is going to be given by answer choice B, not C, again, because keep in mind we have this here, they're both in the numerators. It's not like we are inverting anything, or it's not like the electric flux is in the denominator, so it's not going to be inversely proportional. And then all the other answer choices don't really make sense. For example, A, it is parallel to the electric field. That's not true. Magnetic fields are generally radial, so you can sort of ignore that. And then the other answer choices are saying that nothing about the field can really be determined. That's not true. We've just been able to determine that its magnitude is directly proportional to dE over dt. For number 43, we are told a cross-section of a long solenoid that carries current I is shown above. All of the following statements about the magnetic field B inside the solenoid are correct, except. So let's go through each answer choice here. A, B is directed to the left. Well, if we use our right-hand rule and we sort of wrap our right hand fingers around the direction which the loop is going, we'll see that really the current will actually, or not the current, but the magnetic field will be pointed to the left, which means that's a true statement, which means that's not the answer. For B, an approximate value for the magnitude of B may be determined by using Ampere's law. This is true. This is how we get to this equation, which is given to you on your answer, or on your formula sheet, I should say. And it looks like this. And we use Ampere's law. We use a rectangular loop to figure that out. So that's not true. We can use Ampere's law for that. C, the magnitude of B is proportional to the current I. Well, from this formula here, we know that that's true, so it's not the answer. and then the magnitude B is proportional to the number of turns. Well, that's what this N here, it's the number of turns per unit length, which is exactly what it says here. So that's not true either. And so, well, we know it's going to be E, but let's think about it. The magnitude of B is proportional to the distance from the axis of the solenoid. That's not true. First, you can tell by our formula that none of that is really incorporated, but generally we assume in a ideal solenoid that the magnitude of the magnetic field inside of it will be constant all throughout the inside. Number 44, we're told that the power dissipated in a wire carrying a constant electric current I may be written as the function of I, the length of L of the wire and the diameter D of the wire, and the resistivity P of the material in the wire. In this expression, the power dissipated is directly proportional to which of the following. So when we say directly proportional, that means if we can come up with a formula for it, we expect it to be directly proportional to anything that has an exponent of 1, and it's going to be also in, I guess, the numerator is the easiest way to say it. So let's use the formula here that P is equal to IV. That's, again, given in your formula sheet. And then let's use the fact that V is equal to IR to say that the power is going to equal to I squared times R. Okay, so the next step to know is, well, what is R going to be really equal to? How is it equal to the variables given in the problem? Well, this is another formula given to you in the formula sheet, and it's like this, that the resistance of a wire is going to be given by the resistivity, that's that P looking symbol there, times the length over the area, where area here is going to be pi, and then it's going to be d squared over 4, because we're taking the radius squared, and the radius is half of d. Which then, putting this into that formula right there, tells us that P is equal to I squared times the resistivity times the length over pi d squared over 4. And so when we look at this here, the only two variables that are both, well, that their exponent is 1, even when you're talking about the denominator, the d here has an exponent of -2. That tells us that only L and the resistivity, which is C here, that's the right answer. Those are the only ones that are directly proportional to the power. Number 45 is a classic circuit problem. We're given a circuit here with EMFs and resistances, and we're also told that there is a current in the circuit that's equal to 2 amperes. And then we're asked, what is the resistance of R, which is this resistor down here? Well, we're going to be using Kirchhoff's rules here, and I think the easiest way to start at any point here and go around, count up the voltages, and then solve for R through there. So I like to start sort of at the negative sign here of a battery, of the larger battery that is in this situation. And so we start here with a voltage of 12. And going to the right, we then subtract 6 from this battery right here. And then we're going to be doing here, we're going to be subtracting, and we're using here the formula IR for a voltage across a resistor. That means we're doing 2 times 0.2. And then we're doing 2 times R. This is the mystery variable that we're trying to solve for. Then we do minus 2, 1.5. And then minus 2.3. So a lot going on here. And we can simplify this a bit, but what you'll essentially end up getting at the end is that something that maybe looks something like this when you simplify everything. So 2 is equal to 2R, which tells you that R here is just going to equal 1, and that's in ohms when you solve for that equation right there. So the answer is A. For number 46, we're still working with the same circuit from before. And to solve this question, which is the potential difference between point X and point Y, well, we can use the information from the previous question, but let's not, in case you don't want to rely on previous answers. Well, we know that the current goes in this direction, and looking at the answers here, we're all given the magnitude here. So I'm just going to go from point Y to point X, and generally my answer should be the same. So starting here with point V, let's just basically do the same thing from previous problem. And going to the left here, we run into 2 times 1.5. And so again, that voltage comes from this equation right here. Then, oh, and by the way, I should be subtracting this as well. Let me mention that. Then I'm subtracting 2 times 0.3. And then here, as I'm going across this battery, I'm actually adding a voltage of 12. Okay, and when you work this all out, what you're going to get is a voltage of 8.4. And so the answer here is C. So again, Kirchhoff's rule is going to be sort of our general idea here. For number 47, we are still working with the same circuit from the previous two questions, but this time we're asked how much energy is dissipated by the 1.5 ohm resistor in 60 seconds. So what we need to know here is that E is going to be P times T. Well, really it's supposed to be an integral, but here we can assume that the power is going to be constant. And so T in this case is going to be 60 seconds. We need to figure out what the power is. And so we start off with this equation here from our formula sheet, but then we use the fact that V is equal to IR, which again is from your formula sheet, to get this other form of power, or of the power equation, I should say. We're told in the problem that I is equal to 2, and we are told that this is the 1.5 ohm resistor. So it's just a matter of plugging that all into our calculator here. And what we will get is that the power is going to be 6 watts. And so then plugging that into our formula from before, we're doing 6 watts times 60 seconds. And what we should get is 360 joules, which is answer choice C. For number 48, we're asked that a conducting sphere of radius r carries a charge q, and then another conducting sphere has a radius r divided by 2, and also the same charge. We're told that the spheres are far apart, and then we're asked for the ratio of the electric field near the surface of the smaller sphere to the field near the surface of the larger sphere. Okay, so what we need to know is that the magnitude of the electric field of a conducting sphere is going to be really modeled the same way that we think about point charges, which is to say that it's going to look something like this, okay? Which then tells us that the magnitude for the electric field of the big sphere is going to be K, Q, and then capital R squared. The electric field of the small sphere is going to be given by K, Q, and then we're doing R divided by 2, and then we're squaring, which, well, let me just simplify. That's going to then be R squared over 4, and then let me simplify further and put the 4 at the top. We're looking at something that looks like this. And then you might notice, hey, this looks like it's just this portion right here of this equation, and you'd be correct, which is to say that the electric field of the small sphere is going to really just be 4 times the electric field of the bigger sphere. Okay, and so then if we're being asked about the ratio of the smaller sphere to the larger sphere, then we're asked for E small over E big, and once you work that out, you'll see that that's going to be a ratio of 4, which is E. For number 49, we are given here two charges, negative 2q and positive q, that are located on the x-axis as shown above, and then we're told that this point P, a distance of 3d from the origin O, which is here on the left, is one of the points on the x-axis at which the electric potential is 0. And then we're asked how far from the origin is the other point. And so let's think where this other point would occur. What I'd be thinking is that very close here to the negative 2q charge, the voltage is going to be negative, while very close to the positive q charge, the voltage is going to be positive, which means that somewhere along here, we cross along some point where V is equal to 0. So we need to be looking for a point somewhere in here where the voltage would be equal to 0. So how are we going to do that? Well, we're going to use this formula that once again comes from our formula sheet, and it looks something like this. Let me actually use a little q here. And so this is again a formula from our sheet. And so what we need to figure out is what this R is going to be for each one of them. And also just a matter of plugging into the q. But before we even do that, well, we should say that if this is our first voltage and this is our second voltage, well, V1 and V2 need to add up to 0, okay? So we need to be setting some equation that looks like that. So using that sort of equation, let's figure out the voltage for the negative 2q charge. So we can do K times negative 2q over, and then R is going to be given by, well, if we imagine that at some point that's here, well, then we're looking for this distance. And then we think about, well, we're sort of going along the x-axis here. So this is at point x along the x-axis. Then really what we're doing is x minus d, where d is the distance from here to here. And so that will give us the distance between the charge and the point. Okay, and then we know that this plus the other voltage, which is going to be K times Q. And then now we're going to have to slightly change our formula here. We are still working with the coordinate x here, but now we're going to do 2d minus x, and that will give us this distance right here. and then we set this equal to 0. Okay, then let's actually sort of move this over to the other side, and we're left with kq over 2d minus x is going to be equal to negative 2kq, or actually no, sorry, it's going to be positive now, over x minus d. And then we can cancel out the k and the q like that. And so then let's just move this to this side and this to this side, and then we'll solve for x. So that we are left with x minus d is going to be equal to 4d minus 2x. And then we move over the x's to this side here, and we're left with 3x. And then this is going to be 5d, which is to say that x is going to be equal to 5/3 d. And so the answer choice here that is correct is going to be D. Number 50 was the most missed question in the multiple choice section of the 1993 AP Physics E&M multiple choice. And I'm not sure why. It seems like everything that you need in this question is also in your formula sheet. So let's go over it. We're asked the radial component of the electric field associated with the potential V is equal to A times r to the negative 2, where a is constant. There's maybe a lot of words here that are trying to scare you, like radial component, but really you just have to think about the fact that when you're talking about a point charge, your electric field is going to be radial to that. So really just ask basically about the magnitude here of the electric field. And so if V is equal to A, R, and negative 2, and we're trying to find basically E, well, how do we relate the two? Well, we're given in our formula sheet this formula here, Ex is equal to negative dV over dx. And if we were talking about the radial component, we can treat this instead as something that looks like this, which is, again, very similar to this formula up here. And so then it's just a matter of taking the derivative of this voltage. So taking the derivative with respect to R, and by the way, we're also making that negative, of AR negative 2. Well, this is just calculus. We are going to bring down here the negative 2, and then we are going to also decrease the exponent by 1, which is to say that we're going to end up with 2AR to the negative 3. And that is going to be our radial component right there, which is to say this answer choice is E. Number 51, we are given two concentric spherical conducting shells that have radii R1 and R2 and charges Q1 and Q2, as shown above. And we are asked about R, which is the distance from the center, and we're specifically being asked about this region right here between R1 and R2. And so in the first question of this problem, it's a two-problem question, we are told in this region of the R that's in between R1 and R2, what's the electric field proportional to? Well, really, we're just going to be using Gauss's law here, which looks like this. This is a very important formula, which is to say that we need to be thinking about the enclosed charge in this area right here. And so that's going to be just Q1. If you really think about it, the only charge enclosed is going to be Q1 inside of here. And then our E is going to be, or sorry, I should say we're doing E times 4 pi r squared, and this is equal to Q1 over that, the permittivity of free space constant. Anyways, we don't have to worry about that. We're just asked about things that are proportional, which means let's just ignore all that and all that. What we're left with is that E is proportional to, let me not put an equal sign, it's proportional to Q1 over r squared. That looks like that, which means the answer is going to be A. Number 52 is still using the same scenario from the previous question, but now we're taking up the difficulty a little bit up a notch. We're asked about the electric potential relative to infinity at this region right here. And the reason this becomes more difficult is because there are two different types of electric fields that occur as we're going from infinity to this region. Okay, and so we need to be thinking about both of them and how they affect the voltage. And so for the sake of simplicity, I'm going to be using this formula right here. Or actually, let me use little q again. And the reason I can use this formula is because these spherical concentric shells can basically act as point charges when we are outside of them, which we're going to use to our advantage here. And so the first thing I'm going to be thinking about is the voltage from infinity to just about R2, so to this point right here. And so that's going to be given by this right here. Q1 plus Q2 because those are the charges that are enclosed. Given that we have sort of these two concentric shells, we can treat them as one charge of those two charges, Q1 and Q2. And our R here, well, really we should be integrating like this. And so when we plug in infinity, that's going to be 0, which is to say that the first voltage that we have to worry about is going to be K times K1 plus K2, like this, over R2. Okay, but are we done? No, we're not, because we've just accounted for the voltage that it takes to get from infinity to this point right here. But what about to get into any R that's inside of here? Well, now we need to be worrying about the other voltage. And so, well, when we're inside here, we can basically, because of Gauss's law that we figured out from last problem, we can also just treat it as using this formula, except Q is now just Q1, okay? So let's keep working with that. But now we're going from R2 to, well, just R, any R that's inside of R1 and R2, or between that region, I should say. And now we're doing K times Q1, and we're doing R, and we're going from R2 to R. And so working this out, now it's not going to simplify as easily because of the infinity. What we have here is going to be that V of R2 to R is going to be equal to K Q1. Actually, let me distribute out all of these, and you'll see why. KQ1 over R minus KQ1 over R2, like this. And why is this important? Because we need to now add these two voltages here together. But before we do that, let's just think about how this can be rewritten as this, like this. Okay. Like so. And so then what you'll notice is that when we are combining these two right here, this cancels out with this, which is to say we are left with V of, well, actually V from, I guess, infinity to R is going to be equal to K times Q1 over R plus K times Q2 over R2. And then when we simplify this out, we pull up the K, we are left with something that maybe looks like this. Okay, and so we're at the end of the day being asked what this voltage is proportional to. We can just say it's Q1 over R plus Q2 over R2, which, well, luckily for us is an answer choice. It's going to be E right here. So a very involved problem, probably one of the harder ones in this multiple choice question. It takes a lot of work, but we are able to get the answer either way. Number 53, we are told that we have a battery or batteries connected to two parallel plates that produce the equal potential lines between the plates shown above. And we're asked which of these configurations is most likely to produce these equal potential lines. Well, we don't really have to care too much about most of these equal potential lines. We just actually care about the difference in voltage between this plate and this plate. And well, if you just count, well, that's going to be a difference of 4 volts. Okay, and that's going to be a very big deal, because if this circuit looks anything like this, which is to say it's some batteries or just a battery with a capacitor, then the voltage across here must be the same as the voltage across here. And we know this because of Kirchhoff's rules. Okay, so we need to see which battery combination is going to produce a voltage of 4, first of all. So it's definitely not going to be this. It's definitely not going to be this. That's just 2. And then if we think about this here, actually the voltages will sort of cancel out, and so it's not going to be this either. So now we're working with either B or D. So which one's it going to be? Well, the way that capacitors and batteries work which is to say, if this is the positive side of the battery and this is the negative side, what it does is it sort of carries over that charge to the plate like so. And so let's look back at our question. We are here with the positive side on the right and the negative side on the left, which means that we should expect the positive charge of the batteries to be over here and the negative to be here, which is what D is showing us. B is going to be the opposite scenario. Okay, so the answer choice is D. For number 54, we're still working with the capacitor from the previous question, and we're asked the force on an electron located on the 0 volt potential line is, so imagine we have here an electron of negative charge, keep that in mind. Where would it be attracted to? Well, don't be tricked by the fact that we are here with a 0 volt. It doesn't necessarily mean that the electric field is going to be 0. So we can already sort of reasonably eliminate that, because we know that these capacitors will produce an electric field. And that's going to be in what direction? Well, electric fields always go to an area of lower voltage, which is to say it's going from the right to the left. So does that mean that the electron is experiencing a force to the left? Well, no, because it's an electron. They experience a force that's in the opposite direction, which is to say that the force is in this direction. Okay, so, well, we can eliminate C here and we can eliminate E, right? Because those are seen to the left. And so now we're left to think about, can we actually determine the magnitude of this force, yes or no? And we cannot. And why can we not? Because, well, with this capacitor, we might know the voltage. Well, we know the voltage difference is 4. But does that tell us enough information to figure out what f of E is equal to? Well, f of E, we need Q times E. Well, we know Q is just going to be E, so we have here two E's together. But do we know E? Well, we can relate E and V together using this formula right here, or you might have seen that V is equal to E times D. It's just a reworking of that. And so we know voltage, but we don't know D. We don't know the distance between the two plates. And so that's going to be a big deal. And so that tells us that the answer choice D here is correct, because we do know the direction of the force, but we don't know the magnitude without knowing the distance between the lines, which really is enough to say we don't know the distance between the capacitor plates. For number 55, we're given one of those fun problems that talks about charges and how they move depending on how other charges are surrounding. It's one of the first things you learn in electricity and magnetism. And so, okay, we're told here that we have two metal spheres that are initially uncharged, and they're mounted on insulating stands, okay? And a negatively charged rubber rod is brought close to, but does not make contact with, sphere X. Sphere Y is then brought close to X, and it is allowed to touch, okay? So they do come in contact, and then it is removed, Y, this sphere Y is removed sort of back to, I guess, where it was originally, and then the rubber rod is moved far away from X and Y. So then we're asked what the final charges on the spheres are. Okay, so let's go step by step here, because there's a lot of things going on. So first, X and Y are separated, but the negative charge rod comes close. What happens is that inside of this metal sphere here, which keep in mind it's a metal, so it's conducting, that means charges can move around, we're going to see a buildup of positive charge on the left side and a buildup of negative charge on the right side. And that's because, of course, opposite charges attract, while like charges repel. Okay, then when we bring in this Y here close, and let me redraw it here, what happens is that since they're in contact with each other and they're both metals, these negative charges here, which are electrons, are allowed to move all the way to the Y. Okay, and so if we were to redraw this, this is X and this is Y, what we see here is basically just going to be positive charges, or a large buildup of positive charges on the X, and then a large buildup of negative charges on the Y. Because, you know, the negative charges want to be as far away from this rod as possible. And then when we move the Y away, well, the negative charges will still be built up on the Y, and the positive charges will be built up on the X, which is to say that X is going to be positive, Y is going to be negative. And so the only possible answer here is going to be D. You can also reasonably infer that since the negative rod is never actually brought in contact with X and Y, which means that charges can't transfer between them, then overall X and Y need to be, as a system, need to remain uncharged, which is to say that B cannot be an answer choice and E cannot be an answer choice, because they will not, the spheres X and Y will not add up to be uncharged in total, while A, C, and D do. Okay, but the answer choice is D, and we have worked that out. Number 56 can be a tricky question here. And so it says that the potential of an isolated conducting sphere of radius r is given as a function of the charge Q on the sphere by the equation V is equal to KQ divided by R. If the sphere is initially uncharged, the work W required to gradually increase the total charge on the sphere from 0 to Q is given by which of the following expressions? And we're given these expressions that are very similar to each other, and so that's why this question can be very tricky. But so the first thing to note is that work can be thought of as the change in potential energy, and then using our formula sheet, we are told that, well, potential energy here is going to be given by QV. And so then we can sort of be thinking that work is going to be the change in the Q times the change in V. And then what we want to do is that basically if we're charging a sphere here from uncharged to a charge of Q, we're basically doing a bunch of little work here, a little work of moving one charge to the uncharged sphere and then one more charge into that and another little charge and so on. And so the important thing here is going to be writing this dW, and that's going to be equal to the voltage, the change in voltage, I should say, times dq. Okay, so we're moving a little charge to a voltage here. That's the work that it requires, which is to say if we then are to integrate this, well, we are going to get work when we integrate the dW. But so this V, we can just plug in what we have from the formula to get something like this. And well, what are we integrating it from? Well, we're integrating it, since we're doing it in terms of Q, we're doing it from 0 to big Q, which is given to us in the problem. And so that's exactly going to be answer choice C. Number 57, we are given a circuit as shown above. And we are told that immediately after the switch S is closed right here, we're asked for the current supplied by the battery. Okay, so let's think about what's happening. Immediately after a switch is closed, what's going to be the voltage across this capacitor right here? Because everything else we can just say, well, V is equal to IR, whatever. But the capacitor here, well, at times equal to 0, the voltage across the capacitor is 0. And why is that? It's because the voltage of a capacitor is equal to Q over C. Well, Q in beginning is 0 because we're told that the capacitor is uncharged. Okay, so if the voltage across this is 0, well, current is going to take the path of least resistance, which is to say that if this here is equal to 0, then the voltage across here must also be equal to 0. And that's because a voltage across parallel lines like this are going to be the same. And so if voltage across R2 is equal to 0, that means really no current is passing through it. And you can think about that because of this. So if that's 0, then that must mean, well, the resistance is going to stay the same. It's going to be R2, but it means we have 0 current passing through here. And so all that is to say, we can basically just ignore this and be thinking about the loop as something that works like that. And so then we just use really Kirchhoff's rules here. Well, at least that's how I would do it, to think about it like this. So we're going V in this direction, and then we're subtracting out the current times R1, and that's just going to be equal to 0. We can, again, make the loop. Keep in mind the voltage across this is just equal to 0, and no current passes through here, so we don't have to think about either. Or in other words, the voltage across that is also 0. And so then solving for I, we're just going to get V over R1, which is going to be B. That's the correct answer. Number 58 is very similar to the previous question, except now time is going towards infinity. We're told a long time after the switch has been closed, which is really just a word to say that time has gone towards infinity. And we're asked about the current supplied by the battery. Okay, so in the previous question, we had to think about how the capacitor acted, what the voltage was when time was equal to 0. Now when time is equal to infinity, the voltage of the capacitor isn't necessarily going to be equal to V, but it is going to be enough to mean that there's no current going through here. Okay, so no current is going to be going through here. And so we don't necessarily know yet what that voltage is going to be. But anyways, the voltage that's going across here must also be the same as the one that's going across here. Okay, well, if 0 current is going through here, we can just use Kirchhoff's rules to say that, well, let's just think about the current as going in this direction like that in this loop, which is to say that V minus I and then R1 and then minus I R2, because keep in mind, the current is splitting into, well, here it's 0, and so here it's going to continue being I, which it starts with here. And this is all going to be equal to 0 because this loops around like that. Okay, so then we can just combine the i's into something that looks like this, which is to say that I is going to be equal to V over R1 plus R2. So that means the right answer is A, which is the correct answer. Okay, number 59, we're given, again, a similar problem to the previous one. It's still a circuit, and we're asked about currents, but now instead of a capacitor, we have an inductor. And so how's that going to change our answers? We're asked what the instantaneous current is at point X, which is right there, immediately after the switch is closed, which is to say T is equal to 0. Well, inductors sort of act in opposite ways of capacitors, which is to say, well, before I said that at t is equal to infinity, a capacitor will have zero current passing through it. Well, inductors are the opposite. Inductors will have a voltage that causes the current to be zero when the time is equal to zero. And why is that? It's because inductors basically cause or resist a change in current. And so since this switch S has been open for a long time, we can safely say the current across the circuit is zero, which is to say right after the switch is closed, the inductor is going to fully resist that change in current, and so the current will still be zero. Okay, so then the answer is just A. Pretty simple, because the current that goes across there is still going to be zero. For number 60, we're still working with the same circuit from before, and we're told that when the switch has been closed for a long time, what is the energy stored in the inductor? Okay, so we are given in our formula sheet the equation for the energy stored in a inductor. It's 1/2 times L times I squared. Okay, and L we are given 1/2 is just 1/2, which means we really just need to figure out what I is going to be equal to. And so what is that? Well, we need to be back to thinking about how inductors act in circuits. So the switch has been closed for a long time, which is to say t has gone towards infinity. And what happens to inductors when t has gone to infinity? Well, the voltage across them is going to be zero. So keep in mind the role of an inductor is to resist change in current, but it can't resist it forever. And so after a long time, which is to say infinity, it won't cause any change in voltage, which is to say the current will be acting as if the inductor was not even there. And so that's going to be actually a part of solving this question. So now we need to figure out what is going to be the current through here. Let's just pretend L is not even here. Well, we know the current through here will split up, right? Because of Kirchhoff's rules, will split up, and it will split up equally. Which is a big deal. Which is to say that the I going across X is going to be half of the I that's going across the battery. And we can figure out the one that's going across the battery by simplifying the circuit into an equivalent resistance. So what I'm trying to say here is that if we can combine these two resistors into just one, that will look like this, then this will be easier to figure out. And so Req, well, it's just going to be using this formula here, that the equivalent resistance will be R1 plus R2. And in this case here, both R's are the same. And so what you'll end up getting is that the equivalent resistance will be R/2. Okay, cool. So then we can use Kirchhoff's rules to say that the voltage here minus I times R/2 is going to be equal to 0. And so then that means that I is just going to be 2 times the voltage over R, or 2 times the EMF, like that. And then let's keep in mind that Ix is going to be equal to 1/2 of the I through the battery, which is to say that Ix is going to be the EMF over R. Okay, so then we just plug that in and we get L and then EMF squared times 2 over R squared. And that answer choice is going to be B. That's the correct answer. Number 61, we're still working with the same circuit from the previous two questions, and we're told that after the switch has been closed for a long time, it is then opened at times equal to 0, and which of the following graphs best represents the subsequent current I at point X as a function of time t. Okay, so let's think about this. Once again, an inductor is a part of a circuit that basically resists a change in the current, which is to say if the current originally is equal to 0 and then something happens to it, well, at times equal to 0, the current that's passing through the inductor will still be 0. And only then it will slowly sort of go up to the maximum value that it can have. However, this is actually not the case that I is equal to 0. I is actually going to be equal to whatever maximum current it was, because we're told that the switch has been closed for a long time. And we figured out in the previous question that there was, or in the previous questions, that there was a current passing through this inductor when the switch has been closed for a long time. Which is to say, well, let's just say I is equal to I. And then the inductor will basically be resisting that change. But we can actually already sort of eliminate a bunch of answers here. We know that the current does not start at 0, which means that A through C are wrong. Now we're just left with D and E. And it seems like the only difference is that in E, it's sort of decaying exponentially, while with D, it's sort of linearly, and it seems to sort of reach a point here where it ends. And this is just a fact about circuits, is that they often work with exponentials and I guess natural logs. which is to say that things like charge, voltage, and current are going to change exponentially. Okay, and so we can already reasonably assume that E is going to be the only answer. You could work out a more complicated answer using a function of I with respect to t, something like this. And you'll see that, oh yeah, that decays exponentially. But I would just sort of trust your instincts here in that circuits tend to always be looking something like this, sort of concave up like that. Number 62 is a very simple Kirchhoff's rule question. We're told that a 30 ohm resistor and a 60 ohm resistor are connected as shown above. That means they're in parallel. And they have a battery of EMF of 20 volts and internal resistance R. We're given the current, which is 0.8 amperes, and we're asked what is going to be that internal resistance. Well, what we want to do here, since there's only one battery, is simplify this into just a single circuit with no parallel components, because that makes it a little bit more difficult to work out currents and resistances. And so we need to figure out what the equivalent resistance is of this portion here. And so the equivalent resistance, well, 1 over the equivalent resistance of this, because they are in parallel, is going to be 1 over 30 plus 1 over 60. And when you work this out, you'll basically get that the equivalent resistance is going to be 20 ohms. So that means we can rewrite here this problem to look like so. And we're still with that 20 volts, and we still have here a tiny resistance R, and then we have here 20 ohms. Okay, and so if we have a current here of 0.8 amps, then what we can do is just use Kirchhoff's rule here. We're doing V minus I times R minus I times 20. That's just the resistance of the bigger resistor, and that's equal to 0. And so let's just plug in the values that we know. We know 20 for the voltage. We know 0.8 for that. This should be a small r. We don't know the little r, that's what we're trying to solve for. And then we have here 0.8 times 20, and that's equal to 0. And essentially, when you solve this out, you're going to get that little r is going to be equal to 5 ohms. And so the answer here is C. For number 63, we're given a square loop of wire of 0.3 meters on a side carrying a current of 2 amperes, and it is located in a uniform 0.05 Tesla magnetic field. The left side of the loop is aligned and attached to a fixed axis. And we are asked, when the plane of the loop is parallel to the magnetic field in the position shown above, what is the magnitude of the torque exerted on the loop about the axis? And so this is bringing in a little bit of mechanics into the mix, but that's okay. So the magnitude of torque, well, keep in mind that torque, and you can look over to the mechanics side of your formula sheet for this one, is going to be R cross F, and really these are also vectors technically. And so we need to be thinking about the force that occurs on each side of this loop of wire. Okay, and the force here is going to be magnetic, first of all, because we have a current here that's in a magnetic field. And going back to the electricity and magnetism side of your formula sheet, you'll get that F of B is going to be the integral of I times dl cross B. And technically these are vectors, but really we can just simplify this to I LB, where L is the length. And we can use this, but first let's actually figure out the directions of which our forces will be acting. And so let's start here with this top side here. Using our right-hand rule, we'll see that the current is going in the same direction as the magnetic field, which is to say there's actually not going to be any force here. So no force here, no force here either, because it's still parallel. And so that means that the only ones that maybe have a force is going to be this one here and this one. So let's start with the left side. Using, again, the right-hand rule, current is going up, and then the magnetic field is going to the right. And so what you should get is that the magnetic force should be going sort of into the page, which is to say then that the magnetic force of this should be going out of the page. And you can check that again with the right-hand rule. Okay, the thing is that this magnetic force right here is at a distance of r is equal to 0 away from the axis of revolution, which means that the torque that it provides is 0. Okay, so we can also not worry about that, which means we're really only worrying about the torque produced by this, which is to say, and we can just really just do R times F, because the cross product is, well, it's doing it at a 90-degree angle here. Which is to say we're doing the torque is going to be R times FB, which is to say R times ILB. And so the length is going to be 0.3 meters, and the R is actually also going to be 0.3 meters, and we can tell because it's a square loop, which is to say we're doing 0.3 times, well, the amperes is 2, the length is still 0.3, and then the B is 0.05. And when you put that all in a calculator, what you should get is that it's equal to 0.0090 newtons times meters, which is this answer right here. B is the correct answer. Number 64 is a very classic Gauss's law problem. We're told that we have a solid non-conducting sphere of radius r that has a charge q that is uniformly distributed throughout its volume. And we're told that we have a Gaussian surface of radius little r, which is going to be inside of the sphere, so it's less than big R. And we are using it to calculate the field, the electric field E. Okay, so as you should know, the Gauss's law tells us that E dot dA, the integral of that is going to be equal to the enclosed charge over the permittivity of free space constant. And so what is really the key here is figuring out this enclosed charge, and we can actually just do a shortcut here that's going to make things much quicker for us to figure out. And it's that since this is uniformly distributed, well, we can just then find the volume of the Gaussian sphere and divide it by the volume of the overall charged sphere, and multiply that by the charge q to get us the enclosed charge. And again, we know that because it's uniformly distributed. So you can only really do this shortcut if it's a uniform distribution. So that's to say that q enclosed is going to be q times the v of the Gaussian surface, that's what I'm trying to write here, g, over the, I guess, the volume of the q charge, something like that, which is to say this is going to be 4 over 3 times pi and then little r cubed. Okay, so the Gaussian surface is sort of our imaginary surface here. And then we're doing this over 4 over 3 times pi times, and this is big R cubed, because that's the charge itself, okay? Which is to say that these will be canceling out, and so the enclosed charge is just Q times little r cubed, and then big R cubed in the denominator. Okay, we're not necessarily done yet, though. We just need to think about what this part will be. What is E dot dA? Well, what we're really doing here is we're looking at the surface area of the Gaussian sphere that we made here, and so the surface area of a sphere is going to be 4 pi and then little r squared here. And so plugging this into Gauss's formula, you'll see that we have this on the left side, which is to say, well, we know this is not going to be the answer. And then on the right side, we just do enclosed Q over that constant there. And so you'll see that only this answer choice right here, D, matches our answer. In number 65 here, we're given this illustration here, and we're told that when there is a current I going through X, there is a magnetic field of magnitude B0 at P. And then we're asked what's going to be the magnitude of the magnetic field when there's also a current I going in the same direction as X, but in the rod, or the wire I should say. Well, what we need to figure out is going to be what's the magnetic field produced by a long wire like this. And if you haven't memorized it, you can sort of derive the answer by using Ampere's law. And so we can use Ampere's law here to say that B dot dL, the integral of that is going to be equal to the vacuum permeability constant, I did not remember the name of that, times the enclosed I. And so those two are equal to each other, and then we can just say, well, the dl is going to be 2 pi r. It's a circle of that circumference, and that's going to be equal to, well, just I. And so that's to say that B is equal to that times I over 2 pi r. Okay, so now that we have the general formula for a constant for the magnetic field because of a long wire, let's actually figure out for x, even though we're already told that when the current through I, or through y I should say, is equal to 0, and there's only a current through x, we're told that it's equal to B0, but it's actually going to be helpful for us to sort of recalculate it using this. And so that's to say that B0 is going to be equal to well, we still have a current I, and we're going 2 pi, and then r is just going to be a. That's the distance from here to here. Okay, that's going to be good for us because now we want to figure out what, let's just call it by, is what's the current, or what's the magnetic field caused by the current in y, and that's going to be this, and we're doing 2 pi, and then this is going to be 3a because now the distance is going to be a plus 2a, and so r is just 3a, and so let's just simplify that to say that it's this, which is to say, if you think about it, that the magnetic field produced by y is just going to be equal to 1/3 times b0. Okay, and then the last thing to think about is, are these magnetic fields going to stack? And yes, they are. If you use your right-hand rule, you'll see that they're both going to be acting in the same direction, which is to say that the overall b is going to be by plus b0, which is to say 1/3 b0 plus b0, which is going to be 4/3 times b0. And so the correct answer is going to be D. In number 66, we are told that the north pole of a magnet is first moved down toward the loop of the wire, and then it's withdrawn upward. And we are asked, as viewed from above, what's the induced current in the loop? And so this is going to be forcing you to use the right-hand rule a lot as you're thinking about how the magnetic flux is going to be changing. And so this is sort of also using Lenz's law. So when this is being moved closer, well, we need to be thinking about what the magnetic flux is going to look like. Well, we have these magnetic field lines that should look something like this coming from a magnet. Keep in mind that it goes out of the north towards the south pole. And so as we get this closer, what's happening is that more of these lines are going to be sort of included going through the loop here, which is to say, when the bar is going down, then that means that the magnetic flux, at least as it's pointing downwards, I should say, is going to be increasing like that, which means that the induced EMF, which will produce a current that should oppose this change, okay? So the EMF should then produce a current that will oppose this. And so if you use the right-hand rule, that means it should be creating a magnetic field that's pointing upwards, right? It should be creating a magnetic field that points upwards to oppose that change in the magnetic flux, which is increasing as it's going downwards. And so what's going to cause that is going to be a counterclockwise current. Okay, so at first there's counterclockwise. Now what about when we're withdrawing? Well, then that means that the magnetic flux, at least as it's going down through here, it's going to be doing the opposite of before. It's actually going to be decreasing, which is to say the EMF will produce a current that then will create a magnetic field that's pointing downwards to oppose the change in magnetic flux, okay? Which means that we're trying to make the magnetic flux increase in a sense. And so if you, again, use the right-hand rule, you'll see that the only thing that can produce that, a magnetic field pointing downwards, will be a clockwise motion of the current. And so we're going counterclockwise, I should say, and then clockwise, which means that the answer is going to be E. Number 67, we are told that a variable resistor is connected across a constant voltage source. That's going to be important. Which of the following graphs represents the power P dissipated by the resistor as a function of its resistance R? Well, we're definitely going to need to work with a formula for P, for power. And in the formula sheet, you're given this, and there are two ways to further manipulate this. You can either use the fact that V is equal to IR to get that P is equal to I squared times R, or use the fact that I is equal to V divided by R to get that power is equal to V squared over R. And that's going to be important. And why is that? Because we have a constant voltage in this problem, which means that this will not be changing as R changes, but the current might change as the resistance is changing. So that means that we can just take from this formula that power is going to be proportional to 1 over R. And the only graph here that seems to match that is going to be A. So that's the correct choice. Number 68, we are asked that a point charge Q, shown above, is at the center of a metal box that is isolated, ungrounded, and uncharged. And we're asked which of these statements is going to be true. And I'm going to work actually backwards from E all the way to A, and you'll see why very soon. So starting with statement E, we are told that the electric field outside the box is the same as if it was only a point charge and not the box was there. Is this true? No, it's not going to be true. And so let's see why. So we have here a point charge that is positive, and then we have a box, and it's a metal box, okay? And so that's going to be a big deal, because what happens is that if this is overall uncharged, there's going to be a net negative charge here in the beginning, towards the inner surface, and then there's going to be sort of a positive charge out here on the outer surface. The positive charges need to counteract the negative charges that's inside of the shell, or the box, I should say, because overall it's uncharged. But the negative charge is going to be on the inside, so that the potential inside of the metal box is 0. So that there's no electric field, there's no net charge, and this is just a property of potentials and electric fields inside of conductors. But what this means is that the electric field outside is not going to behave the same way as if it was just from a point charge. So from a point charge, it would be looking radially like this, but the existence of the box sort of messes up a little bit, and it will sort of cause maybe slightly stronger fields here at the corners than what would be expected if it was just a point charge. So no, E is not going to be correct. All right, for D, the electric field outside the box is 0 everywhere. No, this is not true. We're talking about how there is going to be electric fields outside, and the reason for that is because we can use Gauss's law to sort of imagine, well, the enclosed charge is going to be Q, because the metal box is uncharged, the inside is plus Q, so overall there's an enclosed charge of Q. Okay, the electric field inside of the box is constant. This is also not true, and again, we can use Gauss's law. There's definitely an enclosed charge there, and the electric field that's produced is going to look like that. So C is not right. B, the potential inside of the box is 0. No, this is not true for 2 reasons. Well, really just one. For the potential inside the box to be 0, we would probably need there to be no electric field as we go from infinity out to here, and that's not true. We see both an electric field inside of the box and outside as well. And so that leaves us with A. The net charge on the outside surface of the box is Q. And I've actually sort of already talked about this. Using Gauss's law, the encharged Q that's on the surface here, well, given that the box itself is uncharged, but the point charge is plus Q, well, the enclosed charge, I should say, is going to be just Q. For number 69, we're asked which of the following capacitors, each of which has a plate area of A, would store the most charge on the top plate for a given potential difference V. So the potential is going to be staying the same, but the charge is going to differ, and surely the capacitance is also going to differ given the different structures of these capacitors. So what's the equations here that are going to relate all these variables? Well, first of all, we can know from our formula sheet that C is equal to Q over V, which is to say that the charge is going to be equal to the capacitance times the voltage. Okay, so then what's going to be the capacitance? Well, let's go back to the formula sheet. We are told that C is equal to K times the permittivity vacuum constant, and that's multiplied by A, and that's over D. Okay, so then we need to be thinking which of these variables is changing. D is going to change for sure. You can see this here has D and this has D divided by 2. And if you think about it, well, Q is just then going to be K times V, like that, which is to say if D becomes smaller, Q becomes bigger. Okay, so we probably want an answer that has the D divided by 2 as the distance. The A is all staying the same, so we don't have to worry about it. That's just a constant. We don't have to worry about it. The V is constant. So then the other thing to worry about is going to be this K. This is going to be your dielectric constant. And a vacuum is going to have a K of 1. It's going to be the smallest K value. Air is not far behind. It's pretty small. But I'm sure glass is going to have a higher a dielectric constant. It's going to have a higher one than air. And so really, if you're paying attention, we can cross out A and B because of the D, and we're just left with these 3 answer choices. And given this logic here that glass is definitely going to have a bigger dielectric constant than air, we'll see that what will lead to the highest Q will be a smaller distance and a bigger dielectric constant, which means E is the correct answer. We're finally here, number 70, the last question, and it's unfortunately kind of a hard one. Okay, so we're given here a circuit that looks kind of odd, and we're told that the ammeter in the circuit above reads 0. And so we're asked what the resistance is going to be of this resistor. Well, if the ammeter is 0, that means the current going through the ammeter is 0. That's what it measures. So the current here is 0, which also tells us that the voltage from this point to this point is also going to be 0. Because if it wasn't 0, then there would be a current. Okay, so if the voltage across here is 0, then that must mean that the voltage from here to here and from here to here must be the same. Okay, so these voltages here must be the same, and same thing for the voltage from here to here and from here to here. They must be the same, because again, if they're not, then the voltage in between here would not be the same. Okay, so then let's follow sort of how the current would be going. It'd be going here, and then it'd be splitting up into, let's call this I1 and I2 going down here. And we are saying basically that these V's must be equal to each other. Okay, unfortunately though, this is actually sort of difficult for us to work with because we don't know what R. So let's instead actually skip to here, to the currents that's happening here. And what we know is that the current that's passing through this first 3 ohm resistor will be the same that's passing through here. And why is that? Because again, the current across the ammeter is 0. So according to Kirchhoff's rule, all the current that passes through this will also pass through this. And so that means that this voltage here, the voltage across this point, will be the same as the voltage across this point. So we can just use I times 1 ohm. So we're using, again, V is equal to IR. And that's going to be equal to, and again, this is the first current, and this is the second current, is going to be equal to the second current times 2, which is to say that I1 is equal to 2 times I2. And so let me maybe rewrite this, make it a little bit simpler. Let's just call this 2I, and this is just I. And so now going back to the idea from before that this current that passes through this 3 ohm resistor must be the same as the one that passes through the 1 ohm resistor, and vice versa for this, then that is to say that the current or the voltage through here, which is going to be given by 2I times 3 ohms, let me just write it like that, is going to be the same as the one that's passing through the R resistor, which is to say I times R. And so then it's just a matter of solving for R. R is going to be 6, and this is in ohms, and so the answer is going to be E. And congratulations, you've reached the end of the 1993 AP Physics, Electricity and Magnetism multiple choice exam.